What is a reduced order model? And how does this technology enable faster and more accurate digital twins? I'm Asma, Senior Product Marketing Manager at Ansys, and you're watching the Twin Talks. To answer these questions, I'm being joined today by Lucas Boucinha, Lead Product Specialist of Digital Twins at Ansys. Lucas is an expert in the field of reduced order modeling. He has been awarded by the French Computational Structural Mechanics Association in 2013 for his PhD in this field. He won an Ansys CEO Technical Innovation Award in 2019 for his innovation called ROM Framework, or How to Extract Ansys Solver's Magic to Win New Business Markets. He's one of the authors of an Ansys US patent called Systems and Methods for Generating Reduced Order Models in 2022.
Hello, Asma. Thank you for giving me the opportunity to talk about this fascinating topic.
Thank you, Lucas. Can you explain what reduced order modeling is?
Sure thing, Asma. Reduced order modeling is a method used to decrease the computational complexity of high-fidelity models without compromising too much on their accuracy. Then, to understand what is so powerful with this method, first, you need to know what a high-fidelity model is, and second, why you need a lot of computational resources to solve it. Most of the time, a high-fidelity model relies on physical principles to predict complex behaviors, like the deformation of a car crashing against a wall, the air flowing around an airplane, the heat generated by an electric motor, or the electromagnetic interference in electronic devices. Behind the physical principles, there are mathematical equations that are too complex to be solved at hand, except for very simple behavior or geometry. For example, you just need a pen and a piece of paper to solve the equations describing the impact of an elastic ball against a wall, but predicting how a car will permanently deform after such an impact is not possible without a computer.
So a high-fidelity model uses physics to simulate the behavior of industrial objects, and as such, it relies on mathematical equations that cannot be solved at hand.
Exactly. That is why a new field emerged in the middle of last century that is called computational physics. And this new field emerged at the same time as the computer industry started its exponential growth. Researchers from this field invented discretization methods to solve the mathematical equations on which high-fidelity models rely. The idea is to cut geometry into tiny pieces of material called elements on which the mathematical equations are interpolated. The most well-known are the finite element and the finite volume methods. The discretization methods are very generic and leads to a system of equations that can be solved computationally. And this founder, John Swanson, recognized the potential behind these methods and created the first Ansys software in the 70s with the goal of providing general-purpose simulation software that could solve physics-based models of any industrial objects. The main challenge is that with products becoming more and more sophisticated, you need more and more elements to well describe their geometry and complex behaviors. And the system of equations that you must finally solve may contain hundreds of millions of unknowns. This can only be achieved with a lot of computational resources that are used to solve this system of equations in parallel using high-performance computing clusters. It can take a few days or even a week to solve high-fidelity models on HPC clusters with Ansys software.
So from its creation, Ansys provided generic purpose software to solve high-fidelity models. And it could take a long time to get the prediction of the model, even on HPC clusters. I guess this is where model reduction techniques enter the game.
Indeed, Asma, you're right. Model reduction techniques lead to compacted models that are computationally inexpensive to execute and which can be used to obtain results with a similar accuracy as the high-fidelity models. For example, I just told you that a high-fidelity model can take a few days on HPC clusters to deliver its results, while a reduced order model can be executed within few seconds on a laptop to deliver a good approximation of these results.
That sounds like a breakthrough technology. Can you explain why it works so well?
Yes, I can see multiple reasons for that, but let me explain what I think is the main one. The most accepted reasons in the community of why model reductions works so well is related to the regularity you can find in the physical response of a particular system. With discretization methods, simulation software have been designed to be the most generic. Typically, you can simulate the mechanical behavior of a car, a plane, or a bike with the same software. But in many cases, the behavior of the system a given user is interested in can be represented by a few dominant features that reduced order modeling methods perfectly extract. While the high-fidelity model might use millions of degrees of freedom to represent its solutions, the reduced order model can use only a few tenths of them if you focus on the physical response of a particular family of high-fidelity models.
So this means that ROMs works well because it's optimized for the particular application for which it has been created, right?
Yes, great point. You have very well understood, Asma.
So does it also depend on the model reduction techniques that have been used?
Yes, of course. And to talk about the different techniques, I like to distinguish two main families of methods based on the way they impact the software used to build the high-fidelity model. These two families are called the intrusive and the non-intrusive model reductions method. Until the beginning of our century, researchers have been focusing on intrusive methods. These methods are called intrusive because they require access to the internal equations of the high-fidelity model. Doing so is not always possible with an industrial software, and it relies on specific implementation for each solver. That is hard to generalize and requires a lot of effort if you have many high-fidelity solvers like Ansys does. For these reasons, non-intrusive model reductions methods have emerged for the last 10 to 15 years. These methods are also called data-driven since the reduced order model is extracted directly from the high-fidelity model results without touching the software that has been used to generate this training data. And I'm sure you have heard about the ongoing revolution coming from AI tools. These tools rely on machine learning workflows, which consist of two main steps. The first one is the production of the model, and the second step is its consumption. Data-driven approaches are very efficient because you can generate as much training data as needed with the high-fidelity model to reach the targeted accuracy.
So results from high-fidelity model become an infinite source of training data, right?
Indeed, and you could have made this tool on your own. That is the main reason which makes non-intrusive ROM methods so powerful. Also, since the training data come from the physics-based results, they are explainable, which eases a lot the ROM validation process. And as you know, and this has grown for 5 decades by acquiring the best solvers for all fields of physics, and we have decided to industrialize non-intrusive model reduction methods in our product offering.
And what is the level of maturity of this key technology?
We have been building our first release of non-intrusive ROM capabilities on top of 15 plus years of R&D. Our ROM capabilities were first released in the Ansys Twin Builder software back in 2018. And we have pioneered this technology in the simulation industry and filed 2 patents. More than several years later, Ansys provides the state-of-the-art of non-intrusive ROM technology to its customers. But as you know, we never stop innovating at Ansys. And thanks to the ROM experts we have developed in the company to support our customers, we were able to collect a lot of feedback from our user experience. And with our ROM experts, we were able to establish the best practices for creating and validating ROMs with our software. And capitalizing on this acquired experience and feedback, we are now developing our second generation of ROM capabilities in the Ansys Twin AI software.
Now I better understand why Ajay awarded the Ansys ROM framework in 2019. Can you explain the new business opportunities this technical innovation has enabled?
You said earlier, Asma, that reduced order modeling is a breakthrough technology, and you are right. But that is not only a breakthrough on the technical side, it also changes the way simulation software value is delivered to Ansys customers. Traditionally, Ansys simulation software helps optimize product performance. Simulation engineers take advantage of simulation software to help designers optimize their product's behavior against some design criteria. For that purpose, simulation engineers often parameterize the high-fidelity model to simulate multiple product configurations and find an optimal one. Reduced order modeling is a key capability in optimization workflow because with its speed up, it enables optimization routine to test thousands of design configurations and find an optimal one way faster, helping to shorten the overall product design process. Therefore, we can say that reduced order models fasten time to access the final value of simulation software. Another disruptive aspect that finds its root in the machine learning workflow on which our ROM capabilities rely is that you can ease access to simulation software value for non-experts like designers. During the ROM production step, simulation engineers that know well their high-fidelity model can generate training data, then extract and validate ROMs before to export the ROM and share it with non-experts who then directly benefit from the simulation software value without having to know anything about the high-fidelity model details. This allows, for example, a designer to perform real-time what-if analysis just before taking a design decision.
So by providing accurate results in real time, ROMs helps delivering the traditional values of simulation software faster than ever.
Exactly, but there is even more than that. And these ROMs embed simulation software value into autonomous components that can be plugged into larger systems, enabling a possible new ecosystem between manufacturers and OEMs. Suppliers can deliver their components models in the form of reduced order models and share this direct added value with their own customers. This is particularly true for designing the most complex products, which are assembly of very complex components and where a direct simulation of the entire product cannot be done with 3D models. In that case, we could think about replacing some of the 3D components of the product assembly with ROMs and have the remaining model as a co-simulation between a mesh-based solver and ROMs. On the other hand, when system-level models are needed, ROMs are the most complex components can be used to bring 2D, 3D model accuracy inside 0D, 1D system model while preserving the reasonable computational time of system model. This is one of the main strengths of Ansys digital twin solutions, which take advantage of ROMs to extend the traditional simulation software value to the operating life of products. While during the design stage of a product, traditional Ansys users save cost by replacing some physical prototype testing with virtual one, or most innovating customers capitalize on the high-fidelity models they're creating during the design stage to generate even more value for the operating life of their product. They create digital twin model, relying on system model connected with ROM of the most complex components that they connect with their real asset in operation and takes advantage of their ROMs to create virtual sensors, anticipate failure, and implement predictive maintenance. This allows, for example, an operator to predict the impact of the modification of the operating conditions of an asset before taking a decision.
Ansys RUM technology is a key enabler to transform the traditional simulation software business, but also to straighten the emerging digital twin one. Where would you position this little jewel on the Gartner hype cycle?
If you think about the Gartner hype cycle with a peak of inflated expectations, followed by the trough of disillusionment and the slope of enlightenment before the plateau of productivity, I think we are currently solving the two challenges that come with industrial applications, and we are seeing the plateau of productivity not too far in front of us. As I explained earlier, we are currently polishing a second generation of RUM capabilities to make this technology more efficient and available to more users through new workflows. Also, we are taking advantage of our RUM capabilities to overcome the real challenges we've been facing while deploying industrial digital twins.
To conclude, Lucas, can you give an example of such challenges we are currently taking up with the Ansys digital twin solutions?
Sure. One of the main challenges when you deploy a digital twin of an industrial asset is to account for the specificities of the real asset, with mainly its manufacturing imperfections and its past operating life. And since your digital twin model is always an idealization of the real asset, you must adapt it to the real asset behavior. To do so, we introduced the concept of hybrid analytics, which provides the possibility to feed additional data, like sensors data, so that the digital twin models can be further enhanced when being designed and deployed online.
Thank you so much, Lucas, for being part of this second episode of Season 2 of the Twin Talks.
Thank you, Asma. It was a pleasure to talk about reducer model.